Welcome to this online lecture for ECE 201, Introduction to Signal Analysis. The subject of this video is implementation of FIR filters, and the material is taken from section 5.4 of the DSP First text by McClellan, Schaefer, and Yoder. So begin with the equation for an FIR filter, which I think we're pretty familiar with by now. The components of this equation are an input sequence x, which is delayed by a variable unit of time, k. The filter coefficients are the b sub k's. They multiply the x sequence. There's a summation here. K is the index of summation. It goes from 0 to capital M. And then the output, y. So this equation talks about how to construct an output, y, given a set of filter coefficients, b sub k, and an input sequence, n. So it's useful to be able to express an equation like this in terms of a block diagram that we can get a visual picture of. That's always useful. So we construct that block diagram using some building blocks, which are shown here on this page. Well, the basic building blocks are a multiplier, an adder, and a delay, or unit delay. So these three functions, multiplication, addition, and delay, have to be carried out by the computer. The computer has to have a way of doing these three functions. And it has to have a way of doing them very fast, order billions of operations per second. So just like the way we get faster with things that we do, computers developers can speed up the way computers implement algorithms by linking them together and putting them in pipelines so that they do the same thing many times over and over and over and achieve great speed ups in that way. Pipelines is what we call that. Also, we can put things in parallel. We can, if there are not dependencies, if the input of one operation doesn't depend on the output of the previous operation, we can do things in parallel. We can do the two operations at the same time. That's another way of achieving speed up. But one way or the other, we have to implement multipliers, adders, and delays. So when we together into a block diagram that implements an equation or that implements an FIR filter, it might look something like this. This block diagram shows a feed-forward finite difference equation. So there are multipliers here, there are adders, and there are delays. So this line running across here is a delay line. And there are places where we are tapping into the delay line and grabbing values from the computational sequence at those points. And so this is called a tapped delay line. We're tapping in at certain delays and grabbing those values and doing something with them. We are multiplying them by coefficients, the b sub k's, and then we are adding those outputs together. So the equation that this block diagram represents is written down here. This term, b sub 0 times xn, is this part coming down here, and it gets added together to the output of the first delay, x sub n minus 1 multiplied by b sub 1. That's this line coming down here, and that addition is that addition right there. And then this addition is this addition. It is the output of this adder being added to the output of the second delay multiplied by the second filter coefficient, and so on. And so this entire equation reflects the block diagram shown here. So we want to be able to look at a block diagram like this and then write down the equation that goes with it, the equation that it represents. This is only one example of many kinds of block diagrams that we could draw, many ways that we could put together delays and multiplications and additions. And so we want to be able to write down the equations for a particular block diagram. And conversely, we want to be able to draw a block diagram that reflects an equation. So to get a little practice in that, here's another block diagram, an exercise from the book, in which it's the same length of a filter, 3-element filter, three taps, 3 coefficients, actually 4 coefficients. So go ahead and take a minute, stop the video, and write down the equation for this block diagram, and then start the video up again. So hopefully you wrote down an equation which looks something like this. So starting at this end, this term, 3 times x sub n, is this term here. It's being added together with 2 times xn minus 1. That's this part of the equation. This part of the equation represents this leg of the block diagram, where minus 1 is multiplying the output of the second delay, and then this last part of the block diagram, minus 2 multiplying the output of the last delay, is this part. So another way that we can make a block diagram of a system is shown here. This is called the transposed form, and we'll walk through an example of how to write down the equation for this form. The first step is to define variables for the inputs of each of the unit delays, and then we're going to write equations for each of the summations. So if we do that, those equations look like this. So this first equation here is an equation for this summation right here, and it says that y is equal to b naught multiplied by xn plus v1, delayed by 1 time sample. So that is, here's v1 delayed by 1 time sample, and notice that xn has come all the way forward here, multiplied by b naught, and added together with the output of this unit delay. So this is the first equation. The second equation is the output of this adder here. So the two things coming into that adder are b1 times xn, that's coming across the top here, and the output of this unit delay, which is v2 delayed by 1. So that's this part of that equation. Similarly, v2 can be written as the output, or as the sum, of v3 delayed by 1 and then xn multiplied by b2. That's this equation here. And then the last equation is v3 itself, which is just b3 times xn. So we can combine these equations to eliminate some terms. We got a v1 here and a v1 there, and we have a v3 here and a v3 there. So if we do that combination, so this, taking these first two equations and solving, actually substituting this expression for v1 into here and delaying it and substituting it in, we get that the first equation becomes b naught times xn times v1 now, delayed by 1, that's b1x n minus 1, and then v2 n minus 2, that's this part, delayed by an additional 1. And then combining these two equations gives us this equation. v2 is b2 times xn plus v3, but v3 delayed by 1, which is b3 times xn minus 1. That's that term. So now I can combine these two equations to get this equation. I have to delay my V2 in by 2 units. But when I do that, I get this equation for y. So this equation for y is actually the same equation that we had for the block. Let me go back to that. But this one, so this was the feed forward block diagram, and this equation is exactly the same equation as we just came up. Back to that. Okay, so there are some issues with implementation, just to cover them briefly. The block diagram is useful because it shows you how the algorithm is going to be implemented in the hardware, and if there are dependencies. By dependencies, we mean that the input to one part of the algorithm is dependent on another part of the algorithm completing, then that will be shown in the block diagram. Partitioning a filter onto a chip follows the block diagram. So if there are special architectures, they are shown and embodied by the block diagram, and we can rearrange the blocks as necessary, and if possible, in order to speed up our code or optimize it to make it run fast. Another important consideration is if you have a fixed point arithmetic computer as opposed to floating point, you might be aware that fixed point would be integers, whereas floating point would be a floating point number would have a decimal point and is stored in a computer in a different way. You can have round off errors, and you can have overflow or underflow when you do fixed point arithmetic. So this concludes the video on implementing FIR filters in hardware. Thank you for watching.